Oxidation, reduction, reactions. Let's look at the objectives for section 1, the meaning of oxidation and reduction. Define oxidation and reduction in terms of the loss or gain of oxygen and the loss or gain of electrons. State the characteristics of a redox reaction and identify the oxidizing agent and the reducing agent. Describe what happens to iron when it corrodes. Key concepts. How is the gain or loss of oxygen in a chemical reaction linked to oxidation and reduction? How is the gain or loss of electrons linked to oxidation and reduction? What happens to iron when it corrodes? Now, let's look at the vocabulary and practice the pronunciation. Oxidation, reduction, reactions. Redox reactions. Oxidation, reduction, reducing agent, oxidizing agent. Now, let's look at connect to your world. Here is obvious rust of an automobile's undercarriage. During winter in cold climates, salt is often spread on roads to lower the freezing point of water and thereby prevent the buildup of slippery ice. Salt may make driving safer, but the salt that clings to the metallic parts of cars can cause them to corrode or rust relatively quickly. This corrosion is one example of a chemical reaction called oxidation reduction. In this section, you will learn about oxidation reduction reactions. Connecting to your world, discuss and relate. Use visuals. Corrosion. Have students read the opening paragraph. We've done that. How might cars be protected against corrosion? Put a protective undercoat on the car or use plastic car parts. A Bunsen burner oxidizes the methane in natural gas to carbon dioxide and water. So here is the chemical formula. There's methane plus 1 mole of methane plus 2 moles of oxygen yields 1 mole of carbon dioxide and 2 moles of water. What are oxidation and reduction? The combustion of gasoline in an automobile engine and the burning of wood in a fireplace are reactions that require oxygen as they release energy. The reactions that break down food in your body and release energy use oxygen from the air you breathe. Oxygen and redox. Early chemists saw oxidation only as the combination of an element with oxygen to produce an oxide. The burning of a fuel is also an oxidation reduction that uses oxygen. For example, when methane, the main component of natural gas, burns in air, it oxidizes to form oxides of carbon and hydrogen, as shown in figure 20.1. One oxide of carbon is carbon dioxide. Ask students to recall the electron structure of an oxygen atom and how oxygen atoms bond with other atoms. Be sure they identify the source of the electrons an oxygen atom gains during bonding. Point out that when a metal combines with oxygen, it loses electrons, and when oxygen is removed from the oxide of a metal, the metal gains electrons. Explain to students that this knowledge led to a broader definition of oxidation and reduction as an exchange of electrons. Reduction, word origins. Reduction comes from the Latin word reducere, meaning to lead back. Reduction of metal oxides by the removal of oxygen leads to a smaller mass of the metal compared to the original metal oxide. Sometimes when a company reorganizes, it undergoes a reduction in force. What does this mean? A reduction in force occurs when a company reorganizes its structure, leading to a smaller workforce and people losing their jobs. Similarly, a reduction in weight refers to weight loss. Not all oxidation processes that use oxygen involve burning. For example, when elemental iron turns to rust, it slowly oxidizes to compounds such as iron 3 oxide. Bleaching stains in fabric is an example of oxidation that does not involve burning. Common liquid household bleach contains sodium hypochlorite, NaClO, a substance that releases oxygen, which oxidizes stains to a colorless form. Powder bleaches may contain calcium hypochlorite, CaClO with a 2, sodium perborate, or sodium percarbonate. Hydrogen peroxide also releases oxygen when it decomposes. It is both a bleach and a mild antiseptic that kills bacteria by oxidizing them. When charcoal, which is mostly carbon, is burned in air, carbon dioxide and heat are produced. So what is it in air that will combine with the carbon? And the hint is that carbon dioxide is being produced. So I have the carbon and the oxygen, and that's going to yield the carbon dioxide. So it's the oxygen in the air that is going to react with the carbon. So 1 mole of carbon and 1 mole of oxygen will produce 1 mole of carbon dioxide. Give examples of redox reactions and identify oxidizing and reducing agents based on the processes listed in Table 20.1. Emphasize that for a given reaction, one or more of the processes may be in effect. Tell students that the issue of oxidation numbers will be addressed in Section 20.2. Here, have students examine the photograph in the figure and read the caption. On the board, write the balanced redox reaction for hydrogen burning in oxygen. Identify the reducing and oxidizing agents and explain the identities on the basis of partial loss or gain of electrons. State that another gas, acetylene, C2H2, is also used in torches because it produces a large amount of heat when it burns. Have students write the balanced chemical equation for the redox reaction. That's 2 moles of acetylene plus 5 moles of oxygen will yield 4 moles of carbon dioxide plus 2 moles of water. Then have students identify the oxidizing and reducing agents. Ask them to explain their answers. So here is figure 20.3. When items made of iron are exposed to moist air, the iron atoms react with oxygen molecules. The iron rusts. It is oxidized to compounds such as iron 3 oxide. So that's the iron plus the oxygen is going to yield the iron 3 oxide. The oxide of hydrogen is water, H2O. Charcoal, shown in figure 20.2, also oxidizes when it burns, forming carbon dioxide. A process called reduction is the opposite of oxidation. Originally, reduction meant the loss of oxygen from a compound. The reduction of iron ore to metallic iron involves the removal of oxygen from iron 3 oxide. The reduction is accomplished by heating the ore with carbon, usually in the form of coke. The equation for the reduction of iron ore is shown below. 2 moles of iron 3 oxide plus 3 moles of carbon yields 4 moles of iron plus 3 moles of carbon dioxide. The reduction of iron also includes an oxidation process. As iron 3 oxide is reduced to iron by losing oxygen, carbon oxidizes to carbon dioxide by gaining oxygen. Oxidation and reduction always occurs simultaneously. The substance gaining oxygen is oxidized while the substance losing oxygen is reduced. No oxidation occurs without reduction, and no reduction occurs without oxidation. Reactions that involve these processes are therefore called oxidation-reduction reactions. Oxidation-reduction reactions are also known as redox reactions. Checkpoint. What is another name for redox reactions? Oxidation-reduction reactions. The history of the name copper. Reduction processes were used to produce some metals more than 5,000 years ago. Copper oxide and copper sulfate ores were roasted with charcoal to form copper, carbon dioxide, and sulfur dioxide. Large amounts of copper ore were mined on the island of Cyprus off the coast of the area known as Turkey. The Romans, who eventually imported this valuable ore, called it Cyprium, or ore of Cyprus. The name was later shortened to Cyprium and then corrupted to cuprum. The English word copper derives from this corruption of the Latin word for Cyprus. So the island of Cyprus is the origin of the name copper. Electron shift in redox reactions. The modern concepts of oxidation and reduction have been extended to include many reactions that do not even involve oxygen. You learned in Chapter 6 that, with the exception of fluorine, oxygen is the most electronegative element. As a result, when oxygen bonds with an atom of a different element other than fluorine, electrons from that atom shift towards oxygen. Redox reactions are currently understood to involve any shift of electrons between reactants. When magnesium and sulfur are heated together, they undergo an oxidation-reduction reaction to form magnesium sulfide. Applying concepts. Where did the electrons lost by magnesium go? They were gained by sulfur. Oxidation is now defined to mean complete or partial loss of electrons or gain of oxygen. Reduction is now defined to mean complete or partial gain of electrons or loss of oxygen. Redox reactions that form ions. During a reaction between a metal and a nonmetal, electrons are transferred from atoms of the metal to atoms of the nonmetal. For example, when magnesium metal is heated with the nonmetal sulfur, the ionic compound magnesium sulfide is produced as shown in figure 20.4. So oxidation, loss of electrons, gain of electrons. Reduction, gain of electrons, loss of oxygen. If oxidation occurs, reduction occurs. If reduction occurs, oxidation occurs. One does not occur without the other. 2 electrons are transferred from magnesium atom to sulfur atom. The magnesium atoms become more stable by the loss of electrons. The sulfur atoms become more stable by the gain of electrons. Because it loses electrons, the magnesium atom is said to be oxidized to a magnesium ion. Simultaneously, the sulfur atom gains 2 electrons and is reduced to a sulfide ion. So you can see the two electrons filling the outer level of the sulfur. What is the new valence shell of the magnesium? It has 12 electrons and it's giving up 2. So it's going to take on a valence shell similar to neon, and sulfur will take on a valence shell similar to argon. Look at a periodic table and see what happens when magnesium gives up 2 and sulfur takes on 2 relative to the total number of electrons. The overall process is represented as the two component processes below. The oxidation is the magnesium becoming +2 and giving up 2 electrons, loss of electrons, and the reduction is sulfur +2 electrons yields sulfur with a -2 charge, gain of electrons. Losing electrons is oxidation, gaining electrons is reduction. The substance that loses electrons is called the reducing agent. By losing electrons to sulfur, magnesium reduces sulfur. Magnesium is thus the reducing agent. The substance that accepts electrons is called the oxidizing agent. By accepting electrons from magnesium, sulfur oxidizes the magnesium. So review. What's the oxidizing agent? What's the reducing agent? What is oxidized and what is reduced? It all goes hand in hand. It's yin and yang of chemistry, oxidation and reduction. Sulfur is the oxidizing agent. Another way of identifying oxidizing and reducing agents is to remember that the species that is reduced is the oxidizing agent, and the species oxidized is the reducing agent. You might find it helpful to use the following mnemonic device to remember the definition of oxidation and reduction. Leo the lion goes grr. Leo stands for losing electrons is oxidation. Grr stands for gaining electrons is reduction. Redox with covalent compounds. When a metal and nonmetal react and form ions, it is easy to identify complete transfers of electrons. But some reactions involve covalent compounds, that is, compounds in which complete electron transfer does not occur. So what is Leo and what is grr? Leo the lion goes grr. One such example is the reaction of hydrogen and oxygen. 2 moles of hydrogen plus 1 mole of oxygen yields 2 moles of water. Consider what happens to the bonding electrons in the formation of a water molecule. In each reactant hydrogen molecule, the bonding electrons are shared equally between the hydrogen atoms. In water, however, the bonding electrons are pulled towards oxygen because it is much more electronegative than hydrogen. The result is a shift of the bonding electrons away from hydrogen, even though there is not a complete transfer. Hydrogen is oxidized because it undergoes a partial loss of electrons. In oxygen, the other reactant, the bonding electrons are shared equally between oxygen atoms in the reactant oxygen molecule. The welder is using an oxyhydrogen torch to cut and weld steel. When hydrogen atoms burn in oxygen, the redox reactions generates temperatures of about 2,600 degrees Celsius. However, when oxygen bonds to hydrogen in the water molecule, there is a shift of electrons towards oxygen. Oxygen is thus reduced because it undergoes a partial gain of electrons. In the reaction of hydrogen and oxygen to produce water, hydrogen is the reducing agent because it is oxidized. Oxygen is the oxidizing agent because it is reduced. This redox reaction is highly exothermic, that is, it releases a great deal of energy as shown in figure 20.5. Here we have hydrogen and oxygen, and then you have this shift towards The bonded electrons are shifted towards the more electronegative atoms, such as oxygen. And this shift is called a dipole moment. The arrow represents the direction of the shift, and it represents that a dipole moment exists. Developing film. Black and white photography involves oxidation reduction reactions. Exposing black and white film to light activates very fine grains of silver bromide in the film. The film is developed by placing it in a developing solution that is actually a reducing agent. The developer, usually an organic chemical such as hydroquinone, reduces the activated silver bromide to finely divided black metallic silver. Any silver bromide that remains unactivated is removed from the film by using a solvent called a fixer. Sodium thiosulfate, commonly called hypo, is used for this purpose. The areas of the film exposed to the most light appear darkest because they have the highest concentration of metallic silver. The reverse image, called a negative, is used to produce a positive print, the black and white photograph of the image. This is table 20.1, processes that lead to oxidation and reduction. So I'll take the blue rectangles off slowly, and we have oxidation and reduction, and look at each one and see how they're connected, and I'll let this run until it ends. So you can see that each line is related. Increase in oxidation number, decrease in oxidation number. So every line is connected. In some reactions involving covalent reactants or products, the partial electron shifts are less obvious. Some general guidelines are thus helpful. For example, for carbon compounds, the addition of oxygen or the removal of hydrogen is always oxidation. Table 20.1 above lists processes that constitute oxidation and reduction. The last entry in the table refers to oxidation numbers, which are introduced in section 20.2. Checkpoint. What happens to the bonding electrons in the formation of water? They shift towards the oxygen. It's a dipole moment. Billions of dollars are spent yearly to prevent and to repair damage caused by the corrosion of metals. Iron, a common construction metal, often used in the form of the alloy steel, corrodes by being oxidized to ions of iron by oxygen. Water in the environment accelerates the rate of corrosion. Oxygen, the oxidizing agent, is reduced to oxide ions in compounds such as iron 3 oxide or to hydroxide ions. The following equations describe the corrosion of iron to iron hydroxides in moist conditions. So iron plus oxygen plus water, so it's 2 moles of iron plus 1 mole of oxygen plus 2 moles of water yields 1 mole of iron 2 hydroxide. And then the 4 moles of iron 2 hydroxide plus the 1 mole of oxygen plus 2 moles of water will yield 4 moles of iron 3 hydroxide. Oxidation reduction reactions cause corrosion. The copper on this roof reacted with water vapor, carbon dioxide, and other substances in the air to form a patina. This patina consists of a pale green film of basic copper 2 carbonate because patinas enhance the surface appearance of objects. They are valued by architects and artists. Corrosion occurs more rapidly in the presence of salts and acids. These substances produce electrically conducting solutions that make electron transfer easier. The corrosion of some metals can be a desirable feature, as in figure 20.6 shows, resistance to corrosion. Not all metals corrode easily. Gold and platinum are called noble metals because they are very resistant to losing their electrons by corrosion. Other metals lose electrons easily but are protected from extensive corrosion by the oxide coating formed on their surface. For example, aluminum oxidizes quickly in air to form a coating of very tightly packed aluminum oxide particles. Oxidation causes the complete corrosion of some metals. Iron reacts with water and oxygen to form A. Iron 3 oxide or rust. B. Aluminum, however, resists such corrosion because it forms a protective coating of aluminum oxide. Applying concepts, how does the aluminum oxide on aluminum differ from the iron 3 oxide formed on corroding iron? Unlike iron 3 oxide, the tough aluminum oxide coating on the surface of the metal actually protects aluminum objects from further corrosion. Here's figure 20.8. Bridges like this one become unsafe because of the corrosion. They literally fall apart. Corrosion. Discuss and relate. Discuss. Can you identify the common chemical characteristic of all metal corrosion? Let's see. The transfer of electrons from metals to oxidizing agents. Have students cite examples of desirable and undesirable metal corrosion. Ask students to suggest ways in which the rate of corrosion could be decreased or increased. This coating protects the aluminum object from further corrosion as shown in figure 20.7. Iron also forms a coating when it corrodes, but the coating of iron oxide that forms is not tightly packed. Water and air can penetrate the coating and attack the iron metal below it. The corrosion continues until the iron object becomes a pile of rust, controlling corrosion. The corrosion of objects such as shovels or knives is a common problem, but not usually a serious one. In contrast, the corrosion of a metal support pillar on a bridge, as shown in figure 20.8, or the hull of an oil tanker, is much more serious and costly and very dangerous. Painting a surface left protects it from the effects of the environment. Chromium metal also serves as a protective coating and imparts an attractive mirror-like finish on the right. Like aluminum, chromium forms a corrosive-resistant oxide film on its surface. To prevent corrosion in such cases, the metal surface may be coated with oil, paint, plastic, or another metal, as shown in figure 20.9. These coatings exclude air and water from the surface, thus preventing corrosion. If the coating is scratched or worn away, however, the exposed metal will begin to corrode. In another method of corrosion control, one metal is sacrificed or allowed to corrode. in order to save a second metal. For example, to protect an iron object, a piece of magnesium or another active metal may be placed in electrical contact with the iron. When oxygen and water attack the iron object, the iron atoms lose electrons as the iron begins to be oxidized. Figure 20.10, zinc blocks, the white rectangles in the photograph, are attached to the steel iron hull of the ship. The zinc blocks oxidize, corrodes instead of the iron, preventing the hull from corroding. You can see I have little blown up areas of those little blocks, and you have different types as well, different shapes, and they're welded to the ship, the iron hulls. However, because magnesium is a better reducing agent than iron, the magnesium immediately transfers electrons to the iron atoms, preventing their oxidation. Sacrificial zinc and magnesium blocks are sometimes attached to piers and ship hulls to prevent corrosion damage in areas submerged in water. Figure 20.10 shows zinc blocks attached to the steel hull of a ship. The blocks corrode instead of the iron. Underground pipelines and storage tanks may be connected to magnesium blocks for protection. It is easier and cheaper to replace a block of magnesium or zinc than to replace a bridge or a pipeline. Look back at the figure. It's actually very fascinating and an inexpensive investment. What are two ways to control corrosion? Two ways to control corrosion: coating a surface and sacrificing one metal for another. Section 2, oxidation numbers. Determine the oxidation number of an atom of any element in a pure substance. Define oxidation and reduction in terms of a change in the oxidation number, and identify atoms being oxidized or reduced in redox reactions. Section 2, oxidation numbers. Now let's look at the key concepts. What is the general rule for assigning oxidation numbers, and how are oxidation and reduction defined in terms of a change in oxidation number? Vocabulary: oxidation number. Connecting to your world. The bursts of bright white light produced by fireworks are the result of metals being burned. Powdered or flaked aluminum or magnesium are included in the fireworks. When these metals are heated to high temperatures in the explosion, they burn with an intense white light. The fireworks shown here are called stars. As elements burn, their oxidation numbers change. In this section, you will learn about how oxidation and reduction are defined in terms of a change in oxidation numbers. Oxidation numbers. Connecting to your world, discuss and relate. Oxidation changes. Have students read the opening paragraph. We've done that. Check. What are colors? What other colors can be seen in fireworks? Yellow, green, blue, green, red. Okay? Yellow, green, blue, green, and red. Which elements are responsible for these colors? This is fascinating. So yellow would be sodium. We did this in a flame test earlier in the year, if you'll recall. Green would be barium, kind of a pale green, actually. Blue-green would be copper. More of a true green than a blue-green. Crimson, very striking. Crimson is strontium. Assigning oxidation numbers. Relates. Explain that determining oxidation numbers of elements in compounds is a way for chemists to keep track of electron transfer during redox reactions. You're going to have to work backwards. Given a chemical formula, you're going to have to determine oxidation numbers of all the components. What are other examples where items are numbered to keep track of movement? The numbers on sports players' jerseys and the area codes assigned to telephone numbers in different regions are two examples. Excellent. Assigning oxidation numbers. An oxidation number is a positive or negative number assigned to an atom to indicate its degree of oxidation and reduction. As a general rule, a bonded atom's oxidation number is the charge that it would have if the electrons in the bond were assigned to the atom of the more electronegative element. The following set of rules should help you determine oxidation numbers. In binary ionic compounds such as sodium chloride and calcium chloride, the oxidation numbers of the atoms equal their ionic charges. Rule 1. The compound sodium chloride is composed of sodium ions, Na+1, and chloride ions, Cl-1. Thus, the oxidation number of sodium is +1 and chlorine is -1. The oxidation number of any element in the free or uncombined state is 0. The elements shown here, left to right, are white phosphorus, stored under water, sulfur, potassium, stored under oil, carbon, and bromine, liquid and vapor, in an equilibrium state. The potassium and phosphorus are stored under a liquid to prevent them from reacting with oxygen in the air. Rules for assigning oxidation numbers. 1. The oxidation number of a monoatomic ion is equal in magnitude and sign to its ionic charge. For example, the oxidation number of the bromide ion, Br-1, is -1. That of iron +3 ion is +3. 2. The oxidation number of hydrogen in a compound is +1, except in metal hydride such as sodium hydride, where it is -1. So it's it's always +1, except metal hydrides, it's -1. So ionic compounds are easy. You just got to know your compounds. The oxidation number of oxygen in a compound is -2, except in peroxides such as hydrogen peroxide, where it is -1, and in compounds with the more electronegative fluorine, where it is positive. That's interesting. Okay, sounds good. The oxidation number of an atom in uncombined elemental form is 0. For example, the oxidation number of the potassium atoms in potassium metal, K, or of the nitrogen atoms in nitrogen gas, N2, is 0. So that's easy. Uncombined, raw, 0. For any neutral compound, the sum of the oxidation numbers of the atom in the compound must equal 0. Always, always, always. And in the case of a polyatomic ion, the sum of the oxidation numbers would equal the sum of the would be equal to the charge of the polyatomic ion. So phosphate is -3. So the phosphorus and the oxygen would all equal -3 if you added it all up. Okay, for a polyatomic ion, the sum of the oxidation numbers must equal the ionic charge of the ion. Sounds like I just said that. Excellent. Okay. Notice that the sign is put before the oxidation number. Because water is a molecular compound, no ionic charges are associated with its atom. However, oxygen is reduced in the formation of water. Oxygen is more electronegative than hydrogen. So, in water, the two shared electrons in the HO bond are shifted towards the oxygen and away from the hydrogen. Imagine that the electrons contributed by the two hydrogen atoms are completely transferred to the oxygen. The charge that would result from this transfer are the oxidation numbers of the bonded elements. The oxidation number of the oxygen is -2, and the oxidation number of the hydrogen is +1. That refers back to rules 2 and 3. So in water, I can say that. Okay, it's okay. You could say hydrogen and hydroxide, but in this case, you got to follow rules 2 and 3. How a breathalyzer works. This is fascinating. A breathalyzer or breathalyzer is used to estimate the level of alcohol in a person's bloodstream. The chemical potassium dichromate is used in this process. If any ethanol is present in a person's breath when breathing into the apparatus, the chromium +6 in the potassium dichromate orange is reduced to one of the lower states, such as chromium +3, which is green. The color change can be related to the amount of alcohol in the bloodstream. So that's how it's actually calculated. It's actually a redox reaction and related to chromium, such as chromium +6 is reduced to chromium +3. I'll just leave that up there for a few seconds. Yellow potassium chromate and green chromium 3 oxide each have a chromium containing polyatomic ion, inferring what is the oxidation number of chromium in each compound. So let's try to do a little quick math and try to figure out. So the potassium chromate is +6, and the chromium 3 oxide is +3. So how do you get those values? So we know that potassium is +1. That's known. So that's going to be 2 times +1. So that's going to be +2. That's the potassium. Okay. We know that oxygen is going to be 4 times -2. So that's going to be -8. So you have -8 is the negative side, and then it's got to be +8. Well, the potassium is +2. So you say, right, you say the +2 and the -8. So you must have, the chromium must be +6 because it has to be a neutral particle. So the potassium is +2, the chromium is +6, and the oxygen is going to be the -8. Positive has to equal negative. And then the Cr2O3, that would be chromium +3, because the oxygen would be 3 oxygens. 3 times -2 is -6, so it would be +6. And there's 2 chromiums, so each one would contribute +3. So that would be chromium 3. It would be chromium 3 oxide. And this is going to be oxidation numbers, discuss and relate. And we're going to use those same techniques to find the oxidation numbers in the following substances. What are the oxidation numbers of the elements in the following compounds? So let's look at the first one and see if we can figure it out. Potassium nitrate. So it would be -6. 3 times -2 would be -6, so it would be +6. So the potassium is +1, so the nitrogen would be +5, and then the -2. And so you use that same technique use the oxygen, and then the far left one would have a known oxidation number if it was ternary. The P2O5 would be -10, +10, so it would be phosphorus +5, etc. So try to work these out, and you'll need to know this. And it's very straightforward, not a big deal. You have to be able to do oxidation numbers, otherwise you won't know what's been oxidized and what's been reduced in a chemical reaction. Okay, so that is it. Okay, evaluate understanding. You might want to go back and maybe tighten up your understanding of nomenclature. There's some videos that I made that might help you. What does the sign and magnitude of the oxidation number of an element in a compound indicate? What does it indicate? Think of the noble gases. The sign indicates loss plus or gain negative of electrons compared to the isolated element, the neutral charge element. The magnitude indicates the degree of the gain or the loss. If fluorine is converted to fluoride from F2, what is the change in the oxidation number? It goes from 0, that's F2, to -1. Why -1? Because it's gaining electron. It wants to be like neon. Look at the periodic table. Evaluating understanding as we continue. Is this oxidation or reduction? It's reduction, and oxidation numbers are often written above the chemical symbol in a formula. For example, water can be expressed like so. Many elements have several different oxidation numbers. Use rules 5 and 6 to determine the oxidation number of atoms of these elements plus other elements not covered in the first 4 rules. The substances in figure 20.12 are compounds of chromium, but chromium has a different oxidation number in each compound. Copper reacts with silver nitrate. A copper wire is placed in the silver nitrate solution. B, crystals of silver coat the wire, and the solution slowly turns blue as a result of the formation of copper 2 nitrate. Drawing conclusions. What change occurs in the oxidation number of silver, and how does the oxidation number of copper change? The oxidation number of silver changes from +1 to 0. The oxidation number of copper changes from 0 to +2. Oxidation number changes in chemical reactions. Figure 20.13 shows what happens when copper wire is placed in a solution of copper nitrate. In this reaction, the oxidation number of silver decreases from +1 to 0 as each silver ion gains an electron and is reduced to silver metal, Ag, with a 0 charge. Copper's oxidation number increases from 0 to +2 as each atom of copper metal, Cu with a 0 charge, loses 2 electrons and is oxidized to a copper 2 ion, Cu +2. Here is figure 20.14. You look at A and look at B. A redox reaction occurs between iron and copper. A. An iron nail is placed in a copper 2 sulfate solution. The iron reduces the copper ions in solution and is simultaneously oxidized to iron plus 2. The iron becomes coated with metallic copper. So let's read it again. An iron nail is placed in the copper 2 sulfate. So the iron nail becomes, the Fe goes from 0 to plus 2, so that's oxidized. And the copper goes from plus 2 to 0, so that's reduced. So it's a redox reaction where the iron goes from 0 to plus 2, so that's oxidized. And then the copper, which is in solution, plus 2, goes to 0, so that's going to be reduced. So that's the redox reaction that's illustrated in figure 20.14. Here is the equation with oxidation numbers added. So you have 2 moles of silver 1 nitrate plus copper yields copper 2 nitrate plus 1 mole of copper 2 nitrate plus 2 moles of silver. 20.14 illustrates a redox reaction that shows what occurs when a shiny iron nail is dipped into a solution of copper 2 sulfate. You can define oxidation and reduction in terms of a change in oxidation number. An increase in the oxidation number of an atom or ion indicates oxidation. A decrease in the oxidation number of an atom or ion indicates reduction. So let's take a closer look above at the 2 moles of silver 1 nitrate plus copper yields copper 2 nitrate plus 1 mole plus 2 moles of silver. So you can see the silver goes from plus 1 to 0, and the copper goes from 0 to plus 2. So the silver is reduced and the copper is oxidized. Preventing metal corrosion. People spend a considerable amount of time and energy and money trying to prevent or inhibit the simple redox reaction called corrosion. Many metals oxidize when exposed to the oxygen in air. To keep them from corroding or rusting, the metals can be painted, plated with chromium, or galvanized with zinc. But corrosion is not all bad. Because the oxidation of the metal is generally an exothermic reaction, it can be used to generate useful heat, as long as the oxidation takes place quickly enough to release the heat energy in a short span of time. Section 3, Balancing Redox Equations. Describe how oxidation numbers are used to identify redox reactions. Balance a redox equation using the oxidation number change method. Balance a redox equation by breaking the equation into oxidation and reduction half reactions and then using the half reaction method. How are oxidation numbers used to identify redox reactions? How are changes in oxidation numbers used to balance a redox equation? And what is the procedure for balancing a redox equation using half reactions? Vocabulary, oxidation number change method, and half reaction method. Here is aqua regia. This looks like candy actually, but it's actually gold, and we're dissolving the gold in a chemical. Very weird. One of the long pursued goals of alchemists was to change common metals such as lead or copper into gold. One tool that the alchemists employed in their quest was aqua regia, which means royal water. Aqua regia is a mixture of concentrated hydrochloric and nitric acids. When metallic gold is added to aqua regia, oxidation and reduction reactions produce gaseous nitrogen monoxide and stable gold 4 chloride ions. In this section, you will learn how to write and balance chemical equations for redox reactions such as this one. Connecting to your world, discuss and relate. Visuals, alchemists. Have students read the opening paragraph. Done, been there. Were the alchemists making gold? Explain. Were the alchemists actually making gold? No, the alchemists were only combining elemental gold into a gold compound. Elemental gold into a gold compound. Ask students to recall the types of chemical reactions they studied in previous chapters. Write an example of each kind of equation on the board or overhead projector. Ask students to decide which equations represent redox reactions and which do not. Figure 20.15. Many single replacement reactions are redox reactions. Potassium, metal, reacts violently with water to produce hydrogen gas, which ignites, and potassium hydroxide. Zinc metal reacts vigorously with hydrochloric acid to produce hydrogen gas and zinc chloride. Applying concepts. Explain why each reaction is a redox reaction. The oxidation number of potassium changes from 0 to +1, so this is a redox reaction. The oxidation number of zinc changes from 0 to +2, so this is a redox reaction. Identifying redox reactions. In general, all redox reactions can be assigned to one of two classes. One class is oxidation reduction, redox reactions, in which electrons are transferred from one reacting species to another. Many single replacement reactions, combination reactions, decomposition reactions, and combustion reactions are redox reactions. Two examples of redox reactions are shown in figures 20.15. Figure 20.15a shows what happens when potassium metal reacts with water. Figure 20.15b shows the reaction of zinc and hydrochloric acid. The other class includes all other reactions in which no electron transfer occurs. The redox reactions between nitrogen and oxygen takes place when lightning bolts heat the air to extreme temperatures, forming nitrogen monoxide. Remind students of the concepts that underlie the need to balance equations. For all equations, mass must be conserved by balancing the number of atoms, and electrical neutrality by balancing charges. The balancing of redox reactions must also reflect the electrons gained and lost by oxidizing and reducing agents. In other words, electrons cannot be created or destroyed. Ask students for other examples in which balancing is required to achieve conservation. One example is the first law of thermodynamics, which states that energy must be conserved. To conserve energy, any energy change in a system must be balanced by an equal and opposite energy change in the surroundings. For a non-scientific example, consider a checking account. To maintain sufficient funds to cover checks written, money withdrawn would eventually need to be balanced by deposits. When you present the half reaction method for balancing redox equations, students may question why hydrogen ions, hydroxide ions, or water molecules can be added to an equation during the process. Remind them that the aqueous solutions in which these reactions take place contain an abundance of these species. For example, double replacement reactions and acid-base reactions are not redox reactions. During an electrical storm, as shown in figure 20.16, oxygen molecules and nitrogen molecules in the air react to form nitrogen monoxide. This is an example of a combination reaction. The equation for the reaction is shown below. How can you tell if this is a redox reaction? If the oxidation number of an element in the reacting species changes, then the element has undergone either oxidation or reduction. Therefore, the reaction as a whole must be a redox reaction. A color change can signal a redox reaction. When a colorless solution containing bromide ions is added to a solution containing permanganate ions, the distinctive purple color of the permanganate ion is replaced by the pale brown color of bromine. In the example above, the oxidation number of nitrogen increases from 0 to +2, while the oxidation number of oxygen decreases from 0 to -2. Therefore, the reaction between nitrogen and oxygen to form nitrogen monoxide is a redox reaction. Many reactions in which color changes occur are redox reactions. One example is shown in figure 20.17. Written in ionic form, the unbalanced equation for this reaction, written below, you have the permanganate ion, which is -1, and then you have the bromine ion, which is -1, and then the manganese 2 is colorless, and then the bromine is brown, the bromine element, Br2, in the elemental form. It's colorless, or sorry, it's brown. Two ways to balance redox equations. Chemists and chemical engineers must be able to write a correctly balanced equation that accurately represents what happens in a chemical reaction. Many oxidation reduction reactions are too complex to be balanced by trial and error. Fortunately, two systematic methods are available. These two methods are based on the fact that the total number of electrons gained in reduction must equal the total number of electrons lost in oxidation. One method uses oxidation number changes, and other uses half reactions. In a blast furnace like this one, air is blown through a combination of iron ore and coke. The carbon monoxide produced from the oxidation of coke reduces the iron 3 ions to metallic ions. So here's a nice picture, animated picture of a blast furnace. And here's another example of a blast furnace, and the world's largest blast furnace in 1931. Thought that might be interesting. And then you have an animated picture on the left, which explains a little bit further what a blast furnace is and how it works. Using oxidation number changes. You can use oxidation numbers to keep track of electron transfers, a type of chemical bookkeeping. In the oxidation number change method, you balance a redox equation by comparing the increases and decreases in oxidation numbers. To use the oxidation number change method, start with the skeletal equation for the redox reaction. As an example, look at the process used to obtain metallic iron from iron ore in a blast furnace shown in figure 20.18. So here we have iron 3 oxide plus carbon monoxide yields the iron metal plus carbon dioxide. That's unbalanced. So step 1, assign oxidation numbers to all the atoms in the equation. write the numbers above the atoms. So I've done that. Let's look at this a little bit more closely. So let's see if we can spot the redox and the redox reactions, the reduction and oxidation. So the iron goes from +3 to 0, that's the reduction. And what else? The carbon goes from +2 to +4, that's oxidized. Note that the oxidation number is stated per atom. So although the total positive charge of iron ions in Fe2O3 is +6, the oxidation number of each ion is +3. So take a look at that a little bit more carefully. That's not the total charge transfer, but that's the oxidation number of each element. Step 2, identify which atoms are oxidized and which are reduced. In this reaction, iron decreases in oxidation number from +3 to 0 to the change of -3. Therefore, iron is reduced. Carbon increases its oxidation number from +2 to +4, a change of +2. Thus, carbon is oxidized. Step 3, use one bracketing line to connect the atoms that undergo oxidation and another such line to connect those that undergo reduction. Write the oxidation number change at the midpoint of each line. So I've done that there. So there is the carbon, that's the oxidation, +2, and the iron is -3. And that's the reduction. Remember that a change in oxidation number represents the number of electrons transferred. Each carbon atom in CO loses 2 electrons in oxidation, and each iron atom in iron 3 oxide accepts 3 electrons in reduction. As the equation is written, the number of electrons transferred in oxidation does not equal the number transferred in reduction. In a balanced redox equation, the total increase in oxidation number of the species oxidized must be balanced by the total decrease in the oxidation number of the species reduced. Step 4 will make the oxidation number changes equal. Step 4. Make the total increase in oxidation number equal to the total decrease in oxidation number by using appropriate coefficients. Read that again. That's really not as complicated as it sounds. In this example, the oxidation number increase should be multiplied by 3, and the oxidation number decrease should be multiplied by 2, which gives an increase of +6 and a decrease of -6. This can be done in the equation by placing the coefficients 2 in front of the Fe on the right side and the coefficients 3 in front of both CO and CO2. The formula Fe2O3 does not need a coefficient because the formula already indicates 2 irons. So make those changes, and then let's proceed to the next slide. I'll just leave that up for a half a minute as we proceed to the next slide. Okay, so step 5, finally, make sure that the equation is balanced for both atoms and charge. If necessary, finish balancing the equation by inspection. All right, we've done that. So you get 1 mole of iron 3 oxide, 3 moles of carbon monoxide, 2 moles of iron, and 3 moles of carbon dioxide. Using half reactions, this is a different method. A second method for balancing redox equations involves the use of half reactions. A half reaction is an equation showing just the oxidation or just the reduction that takes place in a redox reaction. In the half reaction method, you write and balance the oxidation and reduction half reactions separately before combining them into a balanced redox equation. So here we have sulfur, 1 mole of sulfur, plus 1 mole of nitric acid, and then 1 mole of sulfur dioxide and 1 mole of nitrogen monoxide, and then 1 mole of water. So it's unbalanced. Everything is 1 mole. So now we're going to write the half reactions. There's 2 half reactions, one for oxidation and one for reduction. Here's an interesting table, table 20.2, and it shows the various oxidation numbers of just the element sulfur in a variety of different compounds. I think it's very interesting. Okay, table 20.2, discuss and relate oxidation numbers. Have students read and study table 20.2. What are the oxidation numbers of all the elements in sulfuric acid? Well, it's going to be plus 2, sorry, and then that'll be plus 1 for hydrogen, plus 2 total, so it'll be plus 1, plus 6 for sulfur, and minus 2 for oxygen. Let's look at that a little bit more closely. So in H2SO4, you have the negative charge is going to be negative 8, 4 times negative 2, that's oxygen. And then, so you got to get positive 8. Well, you have a positive 2, the hydrogen is positive 1, and then you have 2 of them, so that's plus 2. So the sulfur will be plus 6. So the hydrogen is plus 1, sulfur is plus 6, and oxygen is minus 2. That's the answer. So I'll leave that up for a minute, let you consider my words. And that's what we have. We have hydrogen is plus 1, sulfur is plus 6, and oxygen is minus 2. What are the oxidation numbers of all the elements in Na2S2O3? Or as they say when the plot's about to thicken, the plot's about to thicken. So we have sodium is plus 1, sulfur is plus 2, and oxygen is minus 2. Remember, left equals right, positive equals negative. Okay, let's look at something different. Redox reactions and rockets. Evidence exists that the use of rockets and of redox reactions to power them began in the 13th century when Chinese armies used arrows of flying fire to defend their cities. These rockets were leather cylinders filled with gunpowder and mounted on sticks. It is generally thought that the gunpowder mixture originated in 9th century China. The essential components of the rocket propellant are a source of energy, the fuel, and an oxidizing agent to react with the fuel. When the mixture is ignited, the fuel is oxidized rapidly and the oxidizing agent is reduced. Gunpowder is a mixture of charcoal, carbon, sulfur, and potassium nitrate. It reacts explosively to produce potassium sulfide, gaseous carbon dioxide, and nitrogen. In the redox reaction, carbon is the fuel and other components are oxidizing agents. The outcome is the same as with the oxidation number change method. To balance a redox reaction using half reactions, write separate half reactions for the oxidation and reduction. After you balance atoms in each half reaction, balance electrons gained in the reduction with the electrons lost in the oxidation. The half reaction method is particularly useful in balancing equations for ionic reactions. Sulfur is an element that can have several different oxidation numbers, as you can see in table 20.2. The oxidation of sulfur by nitric acid in aqueous solution is one example of a redox reaction that can be balanced by the half reaction method. Point out that the underlying assumption when using half reactions is that any redox reaction can always be considered as two separate processes occurring simultaneously. Therefore, the whole reaction can be thought of as the sum of two half reactions. An oxidation reaction and a reduction reaction go through the half reaction method with a specific example, clearly explaining each step. Emphasize that oxidation half reactions are always written with the electrons on the right-hand side of the equation, and reduction half reactions are always written with the electrons on the left-hand side of the equation. Words to live by. Half reactions, discuss and relate. Let's discuss. In step 3, water and either hydrogen or hydroxide can be added to either side of an equation to balance O and H atoms. Explain why these ions can be added to either side of the equation, the H plus and the OH negative, the proton and the hydroxide. The reaction itself is not changed by doing so. Rather, the medium of the reaction is simply being defined. In an acidic solution, H plus ions are present in excess. In a basic solution, OH negative ions or hydroxide ions are present in excess. I'll leave that up for a few seconds, let you digest what I just said, or as the plot is about to thicken, they say, the plot is about to thicken. Choose a balancing method. Let's discuss. A reaction in which the same compound is both oxidized and reduced is called disproportional. When nitrogen dioxide is dissolved in water, it's disproportionate to form nitric acid and nitric oxide. The balanced equation for this reaction is, so there it is, and that's all I'm going to say. 3 moles of nitrogen dioxide plus 1 mole of water yields 2 moles of H plus ions, 2 moles of nitrate ions, and 1 mole of nitrogen monoxide. Bioluminescence. Some organisms produce light by means of oxidation reductions in a process known as bioluminescence. Light is given off when one of a class of compounds called luciferins is oxidized by combining with oxygen. A product of these reactions is energy in the form of light. Bioluminescence serves different functions in different organisms. For example, fireflies use bioluminescence to attract mates, while some squids release a glowing cloud of ink to confuse and escape their predators. So, balancing a redox equation using the half reaction method. I'm going to illustrate the half reaction method very clearly, talking about each step. Step 1, write the unbalanced equation in ionic form. That's key. You got to write it in ionic form. You write the unbalanced equation in an ionic form. Step 2, write separate half reactions for the oxidation and reduction processes. Next, step 3, balance the atoms in the half reactions. Balance the atoms in the half reactions. Step 4, add enough electrons to one side of each half reaction to balance the charges. Hint, the electrons will be added to opposite sides of the half reactions. That's key. Step 5, multiply each half reaction by an appropriate number to make the numbers of electrons equal in both. Step 6, add the half reactions to show an overall equation. That's step 6. Step 7, add the spectator ions and balance the equation. Step 3, balance the atoms in the half reaction. You're just doing that with the spectator ions. The following steps show how to balance this equation using the half reaction method. Step 1, write the unbalanced equation in ionic form. So you can clearly see that the sulfur is going from 0 to +4, and the nitrogen is going from +5 to +2. So the sulfur is being oxidized and the nitrogen is being reduced. Step 2, write separate half reactions for the oxidation and reduction process. Sulfur is oxidized in the reaction because its oxidation number increases from 0 to +4. Nitrogen is reduced because its oxidation number decreases from +5 to +2. So the oxidation half reaction is listed here. Sulfur yields sulfur oxide, so we go from 0 to +4. And then the reduction reaction is going to be the nitrogen from nitrate is going to nitrogen monoxide. So you can separate the nitrogen in the nitrate, and you can separate that. Notice that H plus ions and water are not included in the half reactions because they are neither oxidized nor reduced. However, they will be used in balancing the half reactions. That's a little confusing, but just wait to see what happens. Step 3, balance the atoms in the half reaction. So A, balance the oxidation half reaction. Sulfur is already balanced in the half reaction, but oxygen is not. This reaction takes place in acid solution. So, why is it acid? Because it says aqueous. So water, H2O, and H plus aqueous are present and can be used to balance oxygen and hydrogen as needed. Add 2 molecules of water on the left to balance the oxygen in the half reaction. So now we have to add 4. So oxygen is now balanced, but 4 hydrogen ions, 4 H pluses, must be added to the right side to balance the hydrogen on the left. So that's kind of neat. You can just take them as you need them because you know it's aqueous. I know it sounds a little weird, but it's actually as easy as that. Oxygen is now balanced, but 4 hydrogen ions, 4 H plus, must be added to the right to balance the hydrogen on the left. Excellent. This half reaction is now balanced in terms of atoms. B, this is 3B, balance the reduction half reaction. Nitrogen is already balanced. Add 2 molecules of water on the right to balance the oxygen, NO3. So, oxygen is balanced, but 4 hydrogen ions must be added to the left to balance the hydrogen. So I've done that. This half reaction is now balanced in terms of atoms. Now don't forget, the NO3 is negative charge. So you know that's nitrate and comes from nitric acid. So that makes sense. Step 4, add enough electrons to one side of each half reaction to balance the charges. Note that neither half reaction is balanced for charge. 4 electrons are needed on the right side in the oxidation half reaction. So I'm going to add the 4 electrons on the right. Excellent. 3 electrons are needed on the left side in the reduction half reaction. Okay, good. So that's done. So I have the oxidation half reaction and the reduction half reaction. Excellent. So now let's proceed to Step 5. So each half reaction is now balanced with respect to both atoms and charge. Step 5. Multiply each half reaction by an appropriate number to make the numbers of electrons equal in both. The number of electrons lost in oxidation must equal the number of electrons gained in reduction. In this case, the oxidation half reaction is multiplied by 3, and the reduction half reaction is multiplied by 4. Therefore, the number of electrons lost in oxidation and the number of electrons gained in reduction both equal 12. 12 is the number. So, step 5 continued. So here is the total and final oxidation reaction, balanced, and the reduction, balanced. Now you've got to put it together. So, add the balanced half reactions to show an overall equation. There we have it. Excellent. Then subtract terms that appear on both sides of the equation. Okay, for instance, the electrons, you can cancel that. All right, good. Excellent. Step 7, add the spectator ions and balance the equation. Recall that spectator ions are present but do not participate in or change during a reaction. Because none of the ions in the reactants appear in the products, there are no spectator ions in this particular example. The balanced equation is correct. However, it can be written to show the nitric acid has not ionized. So you can combine the 4H plus and the 4NO3 negatives ones, and you can get the 4HNO3. So you have a balanced equation, nice and neat. Choosing a balancing method. Some redox equations, such as the following example, are simple enough to balance by inspection. Balancing by oxidation number change usually works well if the oxidized and the reduced species appear only once on each side of the equation and no acids or bases are involved. However, in some redox reactions, the same element is both oxidized and reduced. Identify redox reactions, discuss, and relate. Evaluate understanding. The plot thickens. Copper 2 hydroxide is converted to copper 2 oxide and water upon heating. Is this a redox reaction? Why or why not? No. None of the elements undergoes a change in oxidation number. Copper 2 hydroxide, copper 2 oxide. Copper 2 oxide is converted to copper metal upon heating in the presence of carbon. Is this a redox reaction and why? Absolutely, because you are making the metal. So you're going from +2 to 0. So yes. Yes, copper is reduced. Its oxidation number decreases from +2 to 0. Carbon is oxidized. Its oxidation number increases from 0 to +4 when it is converted to carbon dioxide. In the reaction of bromine with a base such as KOH, elemental bromine is simultaneously oxidized from 0 in bromine to +5 in potassium bromate and reduced from 0 in bromine to -1 in potassium bromide. So the reaction listed here. You can tell from the coefficients in the balanced equation that it is not easy to balance. Equations such as this one and equations for reactions that take place in acidic and alkaline solutions are best balanced by the half reaction method. I will leave this up for a moment while you inspect it, and that is the end of this video.